Hello everyone, welcome back to my channel. I'm Joe. 2D tile map is a powerful tool that provides you with a simple way to create a two-dimensional environment based on a grid layout. In 2018.3, Unity is adding support for a new type of grid which allows you to make isometric levels. In this video, we'll have a look at how to create a simple player character movement controller for a 2D game with an isometric perspective. In the scene you will see here, we have our witch character and the simple isometric level which is prebuilt. We will explain how the movement and the animation of the witch character are created. These assets are available for free download at the link in the description below. Also, if you want to learn how to make isometric tile map in Unity, how to use root tile or random tile to save your work, I highly recommend you to watch my previous episodes. Okay, let's get started. Now we have just opened up Unity. You can choose to open the starting project in the description below or open a new 2D project. The project includes one 2D extra folder, environment prefabs, height collider render script, the character and the environment sprites, with a sample scenes with everything set up for you to get started with. Right-click on the hierarchy, choose to create empty game object. Reset the transform component. Add the rigidbody component to this game object. We need to set the gravity scale variable to 0 so that the player is not affected by gravity. And under constraints, we have set freeze rotations on the Z or Z axis to true. This will prevent the player game object from rotating in world space. Then, we can choose to one of which sprites as a child of the which game object. This game object will serve as sprite render and animator. In order to see the witch on the scene, we need to set the sorting layer to foreground sorting layer. We can drag the witch game object and change his position. Also, we can select the witch sprites to scale his size by using rectangular tool. Adding one circle collider 2D component or box collider 2D component in our witch game object. Press the Edit Collider button and edit the collider green circle position and size. Create one C# script called PlayerMovement. Drag this script to witch game object. This script will focus on the player controller. Then create another C# script called PlayerAnimation. This script will focus on how to control the player animation according to their movement. This is the reason why I create one empty game object as a parent of the witch sprite. It will be easy for us to read and control later. Let's first look at how the witch animations are created. Create one new folder called Animation. Select the witch sprite. Press the Create button. We are going to save all of the animations and animator inside the animations folder. Let's first create one animation called Static Nose. Press the red button in order to record our actions. Select the witch sprite game object. Drag the static nose sprite to here, or you can choose to directly drag this witch sprite to the first frame of this animation. Then, we can use the same way to create second animation called Static Northeast. Press the record button and drag the static northeast sprite to here. Then, create the third animation called Static East. Press the record button again and drag Static East sprite to here. Repeat these actions and create 8 static animations in your project. After setting up all of the static animations, we can double check their animations by pressing the play button. Then we are going to create another 8 run animation. Let's first create one animation called Run Nose. Click on the Run Nose folder and select all of the sprites. Drag all sprites to the animation window. When we press play, our animation speed looks unnatural yet. We can change the sample rate to 12. Now our animation looks as well as expected. Create another animation called Run Northeast. Select the correct folder and drag all sprites inside the animation window again. Set the sample rate to 12. Press play. Cool. Create the next animation called Run East. Select the Run East folder and drag all of the sprites inside the animation window. Set the sample rate to 12 and check the animation by pressing play. Create another one called Run Southeast. Find the correct folder and drag all sprites inside the animation window again. Set the sample rate and check the animation. Create the next animation called Run Source. Select Run Source folder and drag all of the Run Source sprites inside the animation window. Set the sample rate and check the result. Create another animation called Run Southwest. Actually, we don't have one Run Southwest folder yet. Well, we can use the Run Southeast sprites to replace. Drag all of the Run Southeast sprites inside the animation window. Change the sample rate, then select the Which Sprite Game object and press the red button again. In the first frame, mark the checkbox next to the FlipX. This checkbox can flip the sprites on the x-axis. We can check the result by pressing the play button. Then we can create another animation called Run West. Drag all of the Run East sprites inside the animation window. Set the sample rate to 12. Press the record button. Select the Which sprite and mark the checkbox FlipX. Next one is Run Northwest animation. Drag all of the Run Northeast sprites inside the animation window. Set the sample rate to 12. Select the Which sprite and mark the checkbox FlipX. However, one point is subtle, so people don't really pay attention to here on the first time. If we translate the animation from Run Northwest to Run Northeast, we have to uncheck the FlipX again, making sure our sprite will face to the correct direction at all times. We can press the record button and double check the FlipX. We want each time when our Which character facing right direction, the FlipX is equal to false. When the Which run in left direction, the FlipX is equal to true. Alright, we have set up 16 animation now. Let's look at how the character movement is achieved. We use the rigidbody.velocity to control our character movement. So we have to get the rigidbody 2D component. We have two public float variables called moveH, moveV. We have another private variable called moveSpeed. This controls how fast the character moves. The default value is 1. We set these variables as serialized field. Serialized field is just used for showing a private variable's value on inspector. You can easily change the value like public variable, but no one can access this value from another script or places. Inside the awake function, we can access the rigidbody 2D component. We are capturing input from the import system into two variables, moveH, moveV. We will scale this by multiplying it by float variable moveSpeed, which can control from the inspector. So we can say rigidbody.velocity is equal to new vector 2, moveH, moveV. The velocity is specified as a vector 2 with components in the x and y directions. Note that update is not called on a regular timeline. If one frame takes longer to process than the next, then the time between the updated calls will be different. FixedUpdate is similar function to update, but it has a few differences. FixedUpdate is called on a regular timeline and will have the same time between calls. Immediately after FixedUpdate is called, any necessary physics calculations are made. FixedUpdate should be used instead of update when dealing with rigidbody. For example, when adding a force to a rigidbody, you have to apply the force every fixed frame inside the FixedUpdate instead of every frame inside update. Update and many other special functions can be created quickly and easily in Visual Studio by using the mono-behavior scripting wizard. In Visual Studio, position the cursor where you want the new function to be inserted. Then press Command or Ctrl-Shift-M to launch the wizard. In the Create Script Methods window, mark the checkbox next to the name of each method you want to add. Choose the OK button to exit the wizard and insert the methods into your code. Using the wizard in this way can help you avoid errors in your code, and also help you to discover what functions are available as you are learning. I don't use rigidbody.move position very often. I can't think of the last time I used this call, but it also works for this project. I also attach to another method to control the character movement in this example. So if I save my script and switch back, we can see that the witch move around the level looks like a ghost and always facing the north. Move to player animation script. First, we have to get the animator component. We will call the animator.Play function, which will transition us immediately to a specified state without blending. We have set up 16 animations. The first 8 animations are static animations. The last 8 animations are run animations. Using curly brackets, we have defined a set of strings which correspond to the names of individual states in the Witch animator controller. Each state contains a reference to an animation of the witch is they are moving or not moving while facing in one of 8 directions. These strings corresponding to state names are what we will use when calling the animator.Play function, which will transition us immediately to a specified state without blending. The sequences of the elements in arrays is correspond to the counterclockwise, which will easy for us to calculate the correct directions later. Each animation or each directions will match with one string element, and we can use this index to play our animation. So where is our character current directions? We can define one vector2 type variable called direction. This direction is equal to new vector2 move h and move v. Back to player animation script, we defined one function called setDirection, which controls each animation state and passing vector2 as an argument. Inside the setDirection functions, we first declare a new empty array of strings called direction array. We then check the magnitude of our direction vector2, which is coming from our player movement. We are trying to determine if the player is moving or not. If the magnitude of direction is less than 0.01, we decide that the player is not moving, and set the direction array is equal to a reference to our static animations array. Otherwise, we will set it to a reference to our run directions array. We need to call the animator.Play functions, which will transition us immediately to the specified states without blending. However, we don't know which one is the last direction of our character. In our variable declarations, we have declared an integer called last direction. This is used as index for the arrays of directions we are selecting from. We will only change the value of last direction if our player is moving. We want our player to maintain their facing directions when they stop moving. This is why two arrays of strings for static directions and run directions must match in terms of directions and the index with index 0 facing north, index 1 facing northwest, and so on so forth. When we stop moving, we reassign the direction arrays to reference run directions and choose the value of last direction based on the current direction vector. The index we choose is calculated by the direction to index function. The purpose of this function is to convert a vector2 direction to a number slice of a circle around the player. We will use the resulting number to select an index from our direction array, passing one vector2 as an argument. Since this function returns one integer type, we can first say return 1 to avoid the red line always stay on this script. We used direction.normalize, which returns this vector with a magnitude of 1. When normalized, a vector keeps the same direction but its length is 1. Since there are 8 directions in this character, and one circle is 360 degrees, each slice should be 360 divided by 8. We want each direction can match with one correct index of this array. Each degree should be matched with one correct index of this array. We create one local float type variable called angle. This angle is equal to vector2.signed angle vector2.up, normal direction. Vector2.up is one direction from bottom to top. As shorthand for writing vector2, 0, 1. The second argument is our character movement direction. Vec2.signed angle returns the signed angle in degrees between A and B. We can put debugger law to test the angle between up and right. We can see the result is negative 90. We can also put debugger law to test the angle between up and left. The result is positive 90. We can also test the angle between up and down. The result is positive 180. Therefore, the result will never greater than 180 degrees or smaller than negative 180 degrees. We want if our character direction is north, which means the angle should be 0 and the index should be 0. If our direction is northwest, which means the angle should be 45, the index should be 1. If our direction is east, which means the angle should be negative 90, and the index should be 6. In this example, we create one offset, and this offset is equal to the half of the step. This variable will be easy for us to calculate the index by using math.flow2int. Angle is equal to angle plus offset. In order to keep the result positive, if the angle is less than 0, we want the angle plus 360. The float type step count is equal to angle divided by step. Finally, don't forget to return the step count. Since we have returned one integer type from this function, we can delete the next line now. This looks like a help function which converts a vector2 direction to an index to a slice around the circle. This goes in a counterclock direction. This is the reason why I initialize the strings arrays by counterclock direction. Back to player movement script. We can call this function by using findObject of type PlayerAnimation.cs direction. the argument should be our current direction. Now back in our project, when we press play, we can see that the widget can walk around the levels while playing appropriate animations in the appropriate perspectives and detect collisions with an isometric environment. Great, we have almost completed the player controller now. We can create another C# script to control our camera. I will directly post the entire camera controller script on here. If you want to know the details about this script, you can watch this episode on my channel. Also, you should adjust the circle collider size, making sure which character can work through each environment. Alright, this is the end of this video. If you want to learn another topic such as how to make isometric tile map in Unity, how to use root tile or random tile to save your work, I highly recommend you to watch my previous episodes. I have published one series of isometric tile map in my channel. I hope this video can enhance your experience using isometric tile map. Stay tuned for future updates from my channel. For more videos about Unity tutorials, Adobe Illustrator, Photoshop and game design, you can click my profile and subscribe to my channel. Thanks for watching, and I will see you in the next video.